So in the previous grammars we have seen that in order to avoid ambiguity in some of the grammars we introduced recursion. So recursion is like this. Recursion is of two types. Recursion can be left recursion, right recursion. Okay, left recursion is like this. If I have any production like this, A derives A alpha or beta, which means the leftmost symbol in the RHS is equal to LHS. The leftmost symbol in the RHS is equal to LHS. This is called recursion. Okay, and in fact it is called left recursion. If I have any symbol on the RHS which is equal to LHS, it is nothing but recursion. Why? A variable is calling itself. Therefore, that is also called as recursive calling. Now, if I have A derives alpha A or beta, it is also a recursion, but this recursion is right recursion. It is also a recursion, but the recursion is left recursion. So left recursion is if the leftmost symbol of the RHS is equal to LHS, then it is called left recursion. If the rightmost symbol of the RHS is equal to LHS, then it is called right recursion. Okay. So if I have left recursion, the problem is this: A derives A alpha, A alpha, A alpha. If you want to stop it anywhere, you are going to stop with beta, right? Or you can directly derive beta, right? Or you can derive 1 alpha, 1 A alpha, which means you can use it one time, 1 A alpha, and then alpha can derive beta, which means beta alpha. Only beta or beta alpha or beta followed by any number of alphas. Therefore, the language generated by this grammar is beta followed by alpha star, which means any number of alphas. Now the problem with this kind of left recursion is, if you see this, if you write it in terms of a function, A is going to call A without doing anything first, which means if you write it as a function, A is going to call A and then going to do some work alpha, isn't it? A is going to call A and then going to do some alpha. A is going to call A and then going to do some work alpha. If you consider that right recursion, it is different. A is going to do some work alpha and then call A. So if you consider these two, here it is going to fall in infinite loop. Left recursion is going to lead to infinite loop, but right recursion, this alpha is going to act as a condition checking, which means there is no way you can fall in infinite loop. The alpha is going to act as an anchor condition. It is going to stop you from falling into it. Now if you consider this language, the language generated by this right recursive grammar is A is going to derive alpha A is going to derive alpha A, and whenever you want to stop it, you can stop it beta. Therefore, the language is alpha star beta. You could either directly derive beta, which means directly beta, or it can be any number of alphas followed by a beta, which means alpha star followed by beta. If I use left recursive grammar, I am going to get this language, but then if I use a right recursive grammar, I am going to get a different language. Most of the compilers, most of them, compiler in the sense most of the parsers, they don't want, especially the top-down parsers. There are two types of parsers, we shall see them later, but there is a class called top-down parser. This top-down parser, they don't allow a grammar, or they cannot work properly if the grammar is left recursive. Therefore, we want to eliminate left recursion without changing the language. Let's eliminate the left recursion without changing the language generated by this. So this right recursion is not equal to this left recursive grammar. The reason is the language is changing. Now I want to have the same language, but I want to have a different grammar, which is not left recursive and which is not this right recursive, right? So the language is, I want beta followed by alpha star. This is the language I want to generate. How can I generate this is, yes, or let us say A only. Variable A has to generate beta followed by alpha star. But if you see this, it is not left recursive, isn't it? Sorry, it is not a grammar at all. The reason is the grammar should not contain stars, right? Alpha star, anything like this. So I want to eliminate the this star and all. So what I do is, I want to generate this language. So A is going to generate beta followed by A dash, and now it is the responsibility of A dash to generate any number of alphas including 0 alpha. See, A is going to generate beta followed by A dash, and now it is the responsibility of A dash to generate any number of alphas including 0 number of alphas. Therefore A dash derives either 0 alphas, which means epsilon, or 1 alpha followed by any number of A dashes, isn't it? So it is a recursion. So which kind of recursion? Right recursion. So understand this. A derives beta followed by alpha star. That is what we wanted. So what I did is A derives beta followed by A dash. Now A dash is going to derive either 0 number of alphas or any number of alphas. Therefore this is the right recursive grammar, which is equivalent to left recursive grammar, this one. A derives alpha A or beta. This is the right recursive grammar, which is equivalent to this left recursive grammar. Therefore, in order to eliminate any left recursion, you have to follow these rules. Let's look at some examples where we have left recursion and we try to eliminate them. One example is this. We have already seen it. E derives E plus T or T, right? So if you look at it, the leftmost symbol of the RHS is equal to LHS, right? Now it is in the form of A derives A alpha or beta. A derives A alpha or beta. It is in the form of that. So what is A and what is alpha and what is beta? If you can identify it, you can directly substitute it here, isn't it? So in this one, A is nothing but E, and alpha is nothing but plus T, and beta is nothing but T, right? Therefore, how can I convert it to this, eliminate the left recursion? See, A derives beta A dash, which means E derives beta, which is T E dash, right? And again A dash derives epsilon, which means E dash derives epsilon or alpha. What is alpha? Plus T E dash. Got it? So this is the equivalent grammar, which is non-left recursive, which is right recursive, and which is equivalent to the original left recursive grammar. Whatever language is generated by this, the same language will be generated by this without getting into infinite loops. Therefore, we have seen the left recursion and we eliminated it. Maybe we shall see 2-3 examples more. Just for the sake of practice, we shall see some examples. Eliminate left recursion from this grammar. Say the grammar is S derives S0, S1, S or 0, 1. I want to eliminate left recursion from that grammar. How could I eliminate it? Is the left recursion? Yes. What is the left recursion? If the leftmost symbol in the RHS is equal to LHS, then it is called left recursion. Now you could imagine it this way. It is nothing but A is S, A derives A, whatever is remaining is alpha, and the other production is beta, the other alternative, right? So you can substitute that in this formula. A is this, alpha, and then beta. Then if you want to convert it into eliminate the left recursion, you have to use this formula, right? You can remember it is a formula or you can derive it. My suggestion is don't by heart anything. So here if you substitute it, what you get is S derives beta A dash. What is beta? 0, 1 S dash, right? And then S dash derives epsilon or alpha A dash. What is alpha? Alpha is 0 S 1 S S dash. That is the elimination. Yes, let's eliminate some left recursion here. There is a left recursion in this grammar, right? So this is A. This production is fine. There is no left recursion. This production is fine. There is no left recursion. There is left recursion in this only this grammar. It is A derives A alpha or beta. Now what is alpha? Comma S. Beta is S dash. If I have the rule A derives A alpha or beta, in order to eliminate it, what is the conversion? A derives beta A dash, and then A dash derives alpha A dash or epsilon. This is the conversion, right? Now here alpha is comma S and then beta is S. Therefore I have to write L derives for this one beta is S L dash, and then L dash derives alpha is comma S L dash or epsilon. So these are the two productions which can be used to replace these these two productions, and this is same. And coming to this grammar, where you have lot of more than one rule in the right hand side, right? More than one rule is having left recursion, and whatever is remaining after that, I am naming it as alpha 1, alpha 2, alpha 3. So the main difference between this grammar and this grammar is we have only one left recursive rule. Here we have many left recursive productions. In this case, that is just extending the previous formula. This formula we are just extending. So we are going to write A derives beta 1 A dash for this production, or beta 2 A dash, or beta 3 A dash. How many ever betas we have, so on. And then A dash derives alpha 1 A dash for this one, alpha 2 A dash, alpha 3 A dash, so on. So that is how we can convert any grammar which is having more than one left recursive productions into right recursive grammars. Okay. So we have seen two classifications of grammars till now. One is ambiguous, unambiguous, and other is left recursive, right recursive. Yeah. So we have seen the grammars are of two types. One is ambiguous, unambiguous, and then we have seen the grammars are of two types. One is left recursive and then right recursive. See, we don't want ambiguous grammars because we are getting more than one parse tree. Therefore, no parsers will really work for ambiguous grammars. So we want only unambiguous grammars. And then we don't want left recursive grammars because the top-down parsers, they will fall in infinite loop. Why? The reason is, if I have A derives A alpha kind of production, A is going to call again A, right? Therefore, it is going to follow infinite loop. So we are not going to use left recursive grammars. And one more classification of grammar is deterministic grammars and non-deterministic grammars. Okay. So what is deterministic and non-deterministic is, for example, if I have the grammar like this, A derives alpha beta 1, alpha beta 2, alpha beta 3. So A, capital A, on seeing alpha, it might go to beta 1, on seeing beta it might go to beta 2. You can assume it that way. That is why it is called non-deterministic grammar. Non-deterministic grammar means we have many options on a single symbol. See, let us assume we have to derive alpha beta 3, right? And if you see the first symbol alpha, and if you see this production alpha beta 1, we might think that this is the right production in order to derive this word alpha beta 3. We might assume that this is the right production in order to derive this. So what we do is we use this alpha beta 1 and then we see beta 3. After seeing beta 3 and beta 1, we'll find out that it is not the right production. Therefore, we have to backtrack again. So that is how the parser will fail. So if I have the second production, see, now I want to generate alpha and the second production is saying that I can generate alpha. Therefore, if I use A derives alpha beta 2, then I'll be able to derive alpha, but later if I have to derive beta 3, it is deriving beta 2. Therefore, at this point I'll know that I did a wrong thing, so I again go back. And again here also, if I use the third production, A derives alpha beta 3, then also same thing happens. I'll see alpha first and then beta 3 first. Yes, now I'll accept it. Now the problem here is we are actually backtracking. This backtracking is happening because of the common prefixes. One or more productions on the right hand side are having something common in the prefixes. This is also called as common prefixes problem or non-deterministic grammars. The problem with non-deterministic grammars is there will be backtracking. If you observe this, why this backtracking has happened, the main reason is we are actually, the main reason is this. We are actually making a decision of which production to choose without seeing enough of the input. See, if the input is alpha beta 3, we are making the decision by only seeing alpha. We should have made the decision by seeing beta 3, right? So if you could see enough of the string which is beta 3 and then make a decision about which one to choose, then there would be no problem. Therefore, I have to postpone the decision making process until I see beta 3. It is also called as left factoring procedure or eliminating non-determinism. So using left factoring is simple. Whatever is common prefix we have, we take it as common and write the remaining part as separately. So I can write it as like this: A derives alpha A dash, and then A dash derives beta 1, beta 2, beta 3. If I write it this way, then what happens is, if I have to generate alpha beta 3, first I don't have any choice, or I don't make any decision at this point by looking at alpha. By looking at alpha, I have only one choice and I'll make it. A derives alpha A dash. I am not making any decision here. And then by looking at beta 3, at later point of time, I will take the right decision, which is beta 3. So what has happened here is, I postpone the decision making till the next part where I could see beta 3, right? So this is called non-deterministic grammar, and this is the equivalent grammar, which is deterministic. And the procedure whatever we used in order to convert a non-deterministic grammar to deterministic grammar is also called as left factoring. Okay, so what is the problem with non-deterministic grammar? Most of the top-down parsers will fail and will have to backtrack if we have non-deterministic grammar like this. So we don't want non-deterministic grammar, we don't want left recursive grammar, and we don't want ambiguous grammars. And we have seen how we could eliminate ambiguity by using disambiguating rules, and how we could eliminate left recursion by converting it using that formula. And now we have seen how to convert a non-deterministic grammar to deterministic grammar using the procedure called left factoring. Okay, so let's see some examples on how to use this left factoring rule in order to convert deterministic to non-deterministic. Yeah, let's see this grammar. And is this grammar non-deterministic grammar? Yes, the reason is, these two productions are having something in common, right? So at least you have I in common. In fact, this IETS and this IETS is entirely in common. So just see what this grammar is. This grammar is, statement can be if expression then statement, or if expression then statement, else statement, or small a or small b, which is nothing but if expression statements, right? So see, this small a is assignment statement. Again, statement can be if expression then statement, or if expression then statement, else statement, or simply an assignment statement, and the expression can be any boolean expression. So that is the statement. Now if I have to generate the word, any word, you can take any word and then generate it. But before, tell me whether it is deterministic or non-deterministic. It is definitely non-deterministic, right? So let us use left factoring and then convert it to deterministic grammar. If I use left factoring, S derives I, E, T, S, S dash, and then S dash derives, for this one it is epsilon. For the first rule it is epsilon, because whatever is there in the first rule we have written it, and S dash need not derive anything. And for the second one, IETS, the remaining part is ES, right? And since we are not doing anything with this A, leave A wherever it was with S, therefore we are leaving it at S. And then E derives small b is boolean expression, right? So now we have converted a deterministic grammar to non-deterministic grammar to deterministic grammar, and this method is called left factoring, right? Fine. And now my question is this: the original grammar, is it ambiguous or not? And then this grammar, is it ambiguous or not? How can you find out whether a grammar is ambiguous? Construct a string, take a string, and then see if you could get more than one parse tree. Let me take a string if expression then statement, else statement. So this is actually not a string, right? The reason is there are even variables here, right? If you look at it, there is a variable S, E, T, S. It is not actually string. There are variables also, which means it is a intermediate string which you get in the process of derivation. If I can show that for this intermediate string, if I can get more than one pass tree, we could just substitute in place of E and S some terminals, and we can see that for the resulting string we are getting two pass trees. Therefore no problem, we can even get two pass trees for this and prove that the grammar is ambiguous. Let's see whether the grammar is ambiguous or not. I am talking about the original grammar. S derives I, E, T, S. I am choosing the first one, and then this S derives I, E, T, S, E, S, right? So this is one pass tree, and let's see if you could get one more pass tree. S derives I, E, T, S, E, S, and then this S derives I, E, T, S. Yes, we got two pass trees, right? Therefore, for a given string, we got two pass trees from the original grammar. So we can say that the grammar is ambiguous. Now, after eliminating the non-determinism, which means after eliminating the common prefixes, we got a new grammar. Now my question is this: eliminating the non-determinism or left factoring procedure, will it eliminate ambiguity also? In the sense, is this grammar unambiguous? So if you have to find out, just take the same string and see how many pass trees we get. For this string, let me see how many pass trees I could get. S derives, one part is I, E, T, S and S dash, and now this S derives I, E, T, S, S dash, and now this S can be ES and this S can be epsilon, right? Which means I got this one from here. And now I will use the same grammar and do one more pass tree. I'll just try. One more pass tree is I, E, T, S, S dash, and now this S dash, the second S dash is again I, E, T, S, S dash, and here I'll use ES here, and here I use epsilon, right? So we got again two pass trees. We got two pass trees for the original grammar for a given string, and we got two pass trees for the second grammar, which is non-deterministic grammar for the same string. Therefore, what we can say is, from these two procedures, we can say that eliminating non-determinism or applying left factoring does not eliminate ambiguity. Therefore, ambiguity will always be there even if you convert a ambiguous grammar into deterministic grammar. So we know the reason for this ambiguity is not actually non-determinism. There is something else. If you observe why we got more than one pass tree here, it is nothing but this else is associated to this if, and this else is associated to this if, which means if I have more than one ifs in this statement, or if I have more ifs more than number of elses, then which if should I associate this else to? The general rule we follow is always else has to be associated to the closest if, which means this else has to be associated with this one. This else should not be associated to the farthest if. The reason why we failed here is, here we are getting two possibilities. One possibility is else is getting attached to the closest if, as well as else is getting attached to the farthest if. This is the problem. What is the root cause of the ambiguity? Ambiguity is not because of the non-determinism, right? So ambiguity is because of the inherent properties of the language. Now what we could do is, we could change the grammar format using disambiguating rules, and then we could see that the grammar is again unambiguous. So this is a classic example which shows non-determinism actually cannot eliminate, determinism cannot eliminate ambiguity. Okay, let's eliminate non-determinism from these grammars. Is this grammar non-deterministic? Are there any common prefixes? Yes, the common prefix is like a minimum, and then you can even see that there are more common prefixes more than a. So my question is this: I know if I have some grammar like this, if I have some grammar like A derives AA and then B derives AB, is this also a common prefix problem, or is this grammar a non-deterministic grammar? No, it is deterministic grammar. The reason is the non-determinism or common prefixes should be present for the same variable. They should not be present across various variables, right? So in this grammar, the problem we have is common prefixes. The reason is the common prefix is present for the same variable, which means more than one productions of the same variable are having a common prefix. Therefore the grammar is non-deterministic, right? So what is the maximum common prefix here? The maximum common prefix is AS. So either you can take these two productions and then pull out AS as common, left factoring, or you could take these three productions and you can go pulling out A as common. Whatever you do, it is not a problem. You can follow any method, you are going to get the same answer, right? So let me say I want to pull the A first. So from the first three productions, from the first three productions I am pulling out A. You can go with any method. A followed by S dash. Now what should this S dash derive? S dash should derive SSBS or SASB or BB. And we are not doing anything with B, therefore leave B wherever it was, right? And what should S dash derive? S dash should derive SSBS or SASB or BB, right? Now is this grammar non-deterministic? No, we still have S as common prefix. Therefore do for one more step. If I eliminate S as common prefix, I could eliminate S as common prefix, which means S dash derives only in this place. S dash derives S followed by S double dash. Now what should S double dash do? Now S double dash should derive SBS or ASB. Therefore if I replace these two productions with these two productions, right, then it is going to be fine. That is eliminating common prefixes. Let's see how to eliminate common prefix from this one, the next grammar. Is this grammar non-deterministic? Yes, it turns out that the grammar is non-deterministic. So what are the common prefixes here? Common prefix is either you can take B as the common prefix or BS as the common prefix in the three. So I'm going to take BS as the common prefix in all three of them, or you could have even taken BSS and BSS as common prefix in the first two productions. I'm going with taking BS as common prefix in all the three productions, right? So first I'll take out BS as common, then what do I get? S derives B, S, S dash. Now what should S dash derive? S dash should derive for the first production the remaining part, second production remaining part, and the third production remaining part. Therefore S dash should derive for the first production what is the remaining part? S, A, S. Or for the second production what is the remaining part? S, A, S, B. Or for the third production what is the remaining part? B, right? Then what about A? We didn't touch A. There is nothing to take out A as common. Therefore leave A wherever it was. Now I got this grammar. Is this grammar non-deterministic? No, it turns out that we still have, this is non-deterministic because it turns out that we still have common prefixes in these two productions. What are the common prefixes here? SA and SA, right? Therefore what I like to take out as common is SA in these two. So leave S production as it is. S derives BS, S dash or A. Leave it as it is. And in the second production S dash, take SA as common. If I take SA as common, then S double dash, and we are not doing anything with B, therefore leave B here. Now what should S double dash be? S double dash be, it should derive AS or it should derive SB. So therefore this grammar is the non-deterministic version, this grammar is the deterministic version for the given non-deterministic version. So you could have followed other method also. Instead of pulling out BS as common initially, you could have even pulled out BSS, and then again we could have done the second step, third step, However, the final grammar you are going to get is the same one, right? You could follow any method. Okay.